Moving on to question 6, it has 6 different parts, A, B, C, D, E, and F. It says solve each quadratic equation and by using factoring and then the zero product property. So real quickly, again, the zero product property, it's pretty powerful. It tells us if we are multiplying two things together, it doesn't matter what they are. I'll just call the two things A and B. And if I get a product of 0, it must be the case that one of these items equals 0. So what we do is there are two things that would be true, right? Either the A is 0 or the B is 0. So we set each part of each factor equal to 0 and solve for x, and we get the two different values x can be that would produce 0 for a given quadratic. Now, A, B, and C are pretty straightforward because they're already in factored form. So all I need to do to figure out what x is, the x that works, is I'm just going to set each of the factors, right? The first one, x plus 7, I'm going to set that equal to 0. And I'm also going to set 2x minus 5, that's the second factor, equal to 0. And then I'm just going to solve for x. So this first equation, if I subtract 7 from both sides, x has to be negative 7. That is one of my solutions. And the other one, if I add 5 to both sides, I get that 2x is 5. And if I divide by 2, x is a positive 5 halves. So my two solutions for this are x is 5 halves and x is negative 7. And again, I didn't need to factor because it was already factored. So those are the values that if I plug into this, right, it would make this whole thing truly equal to 0. And yes, the negative 7 is easy to see because if I do put a negative 7 there, negative 7 plus 7 is clearly 0. This is a little bit more difficult to see, but not much. Right? If I take 2 and I multiply it by 5 halves, 2 times 5 is 10, and 10 divided by 2 is 5. So this becomes 5 minus 5, which is clearly 0. So negative 7 and 5 halves are my solutions. On the next one, again, I'm going to set each of these factors equal to 0. So 3x plus 7 is 0, and x minus 15 is 0. That means that 3x equals a negative 7, and x would be negative 7/3. So that is one solution for that quadratic, and the other one is x is 15. So if I plug either value in to that, it would produce 0. In the case of the negative 7/3, it would make this part equal 0, so it doesn't matter what the second part is. And in the case of the positive 15, it would make this part equal to 0, so it doesn't matter what the first part is. All right, and then finally, question C. I say finally, it's the three simple ones that don't need to be factored. Then we need to talk about factoring a bit. So again, it's just x plus 11 is 0, therefore x is negative 11. And 3x plus 15 is 0, therefore 3x is negative 15, and x is negative 15/3, and that reduces, right? So x is negative 5. So if I plug in negative 5, this part becomes 0. Yeah, that's negative 15 plus 15. And if I plug in negative 11, this part becomes 0. So those are our two solutions. So A, B, and C are done. Now let's move on to the bottom three. The next three, I can see that it is equal to 0, right? It's just a matter of us factoring it so we can use the zero product property. So I'm going to go ahead and sketch out a real quick generic area model. And my goal here is just to rewrite this side of the equation. Right now it's written as the sum of the parts of an area model, and I want to rewrite that as the product of a length times a width. I've decided to clean that up. I don't know why I didn't like that. That's beautiful. And in my area model, I can see that I've got an x squared, check. And I can also see I've got a positive 2, check. Now, these other two boxes have to sum up to negative 3, right? When I add them, they have to be negative 3x. I need to be real specific, negative 3x. And the other thing that we observed in chapter 4, right, was that these products, right, this product is always equal to this product, in these. So I know that when I multiply, I have to get 2x squared. So that's where this diamond problem comes from, right? If you look at this, I'm looking for two things such that when I add them up, they equal negative 3x, right? Because again, this area, the parts have to equal x squared minus 3x plus 2. But also when I multiply, it has to be a 2x squared. So two things that give me a product of 2x squared and a sum of negative 3x. And I believe what I'm looking for is a negative 2x and a negative x. So they're both negative in this case. Um, if I were to multiply those, right, negative 2x times a negative x would give me positive 2x squared, which was what I need because the diagonals have to be the same. And the other thing that would have to happen is when I add those, negative 2x minus x, I have to get negative 3x because that's this part. And I have that. So I'm going to write this down as a negative 2x and a negative x. And you can see at this point, now I put my final check mark there. Those three pieces I have, x squared minus 3x plus 2, are represented in my area model, right? When I look at my area model, all of those pieces add up exactly to that trinomial. So now I'm going to go ahead and factor this. And when I do that, I can see, I'll just go ahead and write an x and an x here. X times x is x squared. Now, if I'm looking at my negative x and the x across from that, this has to be negative 1. And if I'm looking at the x and the negative 2, this has to be a negative 2. And if I look at each of the pieces now, yeah, when I multiply negative 2 times negative 1, I do get 2. When I multiply x times x, I do get x squared. And negative 2 times x is negative 2x, and negative 1 times x. So everything matches up perfectly here. So now I can rewrite this equation as, instead of a sum of the parts, I can write it as a product of the length and width of the area model. So I can write it down as x minus 2 times x minus 1. So here you see the length times the width equals the area of that rectangle. Now what's nice about it is looking at it as the product of its dimensions, its length times width, is I can easily see the values of x that make this true by just setting each of the respective factors equal to 0 and solving. So x will either equal positive 2 or whoa, that glitched just a bit. Sorry about that. Or x minus 1 equals 0. So x would equal positive 1. So the values that make this true are positive 1 and 2. And there's a way that I can check this visually on my graphing calculator. I'm going to go ahead and do that. I'm going to graph the related quadratic equation. And let me turn this on. That would be y equals the x gets squared. It is positive. So I could say x squared and then minus 3x and then plus 2. So if I look at the graph of this, right, the places where it equals 0 are the places where it's crossing the x-axis. And that's what this equation is saying. It's saying, look, I've got this x squared minus 3x plus 2. I want to know when that thing is 0, when it equals 0. And I can see them there. They're happening along the x-axis. So I claim that they happen at 2 and 1. And I can verify that by just hitting trace, entering 2. And when I do it, you can see, yep, y is 0. And if I was to enter a 1 and press enter, you can see there's the other one. Y is again equal to 0. So those are the two values of x that make this equal to 0. On the next one, I'm going to go ahead and add 16 to both sides. This is the difference of two squares. And I can solve this by writing it as, it is x plus 4 times x minus 4. That's the difference of square patterns. And if I set each of these equal to 0, I would get x is negative 4 for the first factor, and x equals positive 4 Again, setting each of these, this equal to 0, set this equal to 0, and then solving. The other thing I could do is because there's no linear term, I can just rewrite this as x squared equals 16, and then I can take the square root of both sides. Now, in this case, I need to be careful. Remember, there are two roots. There are two things that I can square to get 16. So when I take the square root of both sides, I indicate both of those, right? It's plus or minus 4. So 4 squared is 16, but also negative 4. Again, negative 4 times negative 4 is 16. So those are my two roots. And that's my solutions, right? As x is negative 4, x is 4, or we can write down x is plus or minus 4 in the case because this was a perfect square. And then finally on f, same thing, right? I'm going to go ahead and look at a generic area model. And I'm going to try and transform this. Right now it's written as the sum of the parts. It's got a 3x squared. It's got a positive x and it has a negative 10. So I've written down my quadratic corner and the linear corner. And now I need to rewrite this x into two parts such that I can, it goes back to this diagonal feature, that this diagonal is, that's too wide, that the both of the diagonals have to equal 3x squared. I'm sorry, negative 30x squared, that's correct. So the diamond problem again looks like this. When I add these two things up that I fill in the missing boxes, it has to have a sum of x, and it has to have a product of negative 30x squared. And I'm immediately thinking of 5 and 6 because I know they differ by 1, and I know 5 and 6 are obviously factors of 30. And I'm going to go with the positive 6 times x and a negative 5 times x. So visually I can see that when I multiply those, I do get negative 30x squared, and when I add those, I do get a sum of positive 1x. So I'm going to fill these in. This should be 6 times x and negative 5 times x. So, all right, so let's go ahead and I guess I'm going to pull out this greatest common factor going down first. It's kind of important this time. And I'll write this as a 3x. And then off to my left, I'm just going to write this down as an x. So that's true. 3x times x is 3x squared. Since it's 3x down below there, this has to be the number 2. And since this is x, this has to be a negative 5. And again, I'm just verifying that the dimensions are correct. So x times 3x squared is 3x. I'm sorry, x times 3x is 3x squared. 2 times 3x is 6x. 2 times negative 5 is negative 10. And x times negative 5 is negative 5x. So I can now transform this equation. It's written as a sum of parts, and I'm going to write it as the product of a length and width. So I can say length and width, x plus 2 times 3x minus 5 is equal to 0. Length times width is the area. So again, this is not magic. I'm just saying this is two different ways to write this, right? Length times width, and then that is the area. So in this form, right, when I'm writing it down and looking at it as the product of the length and width, it's much easier for me to see what my values of x are that would make this 0 because of the zero product property. So I set these each equal to 0. So I write x plus 2 is 0, therefore x is negative 2. And I write 3x minus 5 equals 0, therefore 3x is 5, and x is positive 5/3. So my two answers are x is negative 2 and x is 5/3. And again, I'm going to go ahead and verify that with the calculator. So I'm going to turn this on, clear the last equation for my y equals, and I just want to write 3x to the second power plus an x and then minus a 10. And now that I'm looking at that, I can go ahead and graph that function. There it is. And I can hit trace and I can enter a negative 2. And when I enter a negative 2, it tells me y is 0. Hooray. And I'm also going to enter a, I'll do parentheses, 5 divided by 3. And when I enter 5/3, it tells me y is 0 also. So those two values, right, totally do make this thing equals 0, right? Both -2 and 5/3 equals 0. And I was, again, verifying it by looking at the related quadratic function. And I feel very good about all 6 of those, A, B, C, D, E, and F.